Okay, Assalamualaikum and good morning. So here I am trying my best to deliver the description of hybridization to all of you. Okay, now, as we know, last week we have you able to identify the type of hybridization, yeah. But today I want to continue with the description of hybridization. Let me start with BECL3, BECL2. Sorry. Okay, we have BECL2. Whatever it is, you must start with the right Lewis structure and determine the right shape. This is essential and compulsory, compulsory, so that it will be easier for you to check your drawing at the end of the day. Okay, now um, the structure of BECL2 is like this. Basically, you must draw it on your own, starting from the very beginning, and then determine the right shape. In this case, the shape of BECL2 is linear. Right. Let's start with the central atom. Beryllium, in its ground state, has two valence electrons in the second period, 2s and 2p. 1, 2. Right now, remember, in order to form covalent bond, beryllium needs to have two unpaired electrons. Yeah, because it forms two covalent bond with fluorine atoms, it needs two unpaired electrons. So the clue is to check how many unpaired electron you need. You refer to the number of sigma plus pi. Right? Okay, sigma in this case, there are two sigmas and no pi. Hence, 2 plus 0 equals to 2. This is not part of the working. This is just a clue for you. Okay, now, since we need two unpaired electrons or two single electrons, one electron here needs to be promoted. Yeah, it needs to be promoted to a higher energy level, to the empty p orbital here. So what will form is something like this. Beryllium 2s and 2p. Since it is disturbed, it is disturbed, therefore it is now unstable, which means it is at excited state. Something unstable must return or regain its stability, and in this case, the orbitals need to hybridize. How many will hybridize? How many orbital will hybridize? That depends on, okay, just like what I mentioned last week, it depends on the number of sigma plus lone pair. Okay, two sigmas, okay, refer to the Lewis structure. We have two sigmas and no lone pair. That means it is still 2. Now, we count 1. We count from the first orbital, that is S. Yeah, 1, 2. That means the orbitals that are involved in the hybridization are, okay, 1, 2, and we call that orbitals as P. The other two remain in the form of pure orbital. Yeah, this one remain, and these two become SC. Hybrid orbitals are degenerate orbitals. That means, excuse me, the orbital diagrams must be close to each other, to show that they have equivalent energy. Right. And then the terminal atom. The terminal atom is chlorine. This year we only focus on the hybridization of central atoms. Yeah, that means this year your terminal atoms will all use its pure orbitals. 2s, oh sorry, chlorine is in period 3, so 3s and 3p and 2, 3, 4, 5, 6, 7. That means the single electron is in 3p orbital, which will overlap with the hybrid orbital of beryllium. Now let's sketch. We sketch beryllium first. Beryllium has sp. How many sp? 2. That means 2 hybrid orbitals for beryllium. And how does a hybrid orbital looks like? One hybrid orbital looks like this. So if we have 2, it looks something like this. Remember, sp has AB2 configuration or arrangement. That means the shape will be linear. sp2 has AB3 arrangement. Therefore, the shape is trigonal, planar, and so on. Let's go back to BeCl2. Now we have, okay, you can omit the tiny lobe in your drawing. You can leave the tiny lobe out. We have 2 unpaired electrons here. And this is Sp, and this is another S. This is beryllium. And remember, beryllium overlaps with 3p orbital of chlorine. Okay, 1 Cl on this side, and this is 3p, and another Cl on the left hand side. This is 3p. Alright? Okay. This is how your orbital overlapping diagram looks like for BeCl2. Okay, it should have the same shape as the one we predicted before. Yeah, sama kan? Alright, let's have a look at second example. Okay, let's try something with lone pair. Yeah, something with a lone pair. Now we have okay, what should I try? Okay, let's try H2O. Yeah, H2O. Something very simple so that you can understand what's going on clearly. Okay, the central atom is oxygen, and if you draw the Lewis structure, it will be like this, and the shape is bent or B shape. Okay, O, ground state. 6 electrons, 2s, 2p, 1, 2, 3, 4, 5, 6. Then, what do we consider? Remember, we look at the number of sigma plus pi. There are 2 sigmas and no pi. So 2 plus 0 is 2. That means we need 2 unpaired electrons or single electrons. Do we have 2 single electrons? Yes, we do. Therefore, there won't be any excited state, or if you want to rewrite, it will be the same configuration as the ground state of oxygen. Sama. Actually, yalah. But just so that you have the same flow, And then the next step, you refer to the number of sigma plus lone pair and 2 sigmas plus lone pairs. Altogether is 4. Okay, now starting from S, you count 4. Here 1, 2, 3, 4. That means all orbitals here will hybridize and form 4 sp3 orbitals. 1, 2, 3, 4, 5, 6. And what about the terminal atom? The terminal atom is the hydrogen. And hydrogen has the configuration of 1s1. Okay, let's sketch oxygen. Oxygen here has sp3, yeah, shape or sp3 hybridization. sp3 is 4. That means the shape is or the arrangement is tetrahedral. Something like that. This is oxygen. And remember, where? Okay, this one is lone pair, single, single. Where do you place the lone pair? Remember, finally, the shape must be V, like this. So if I have the lone pairs here and here, then I will get my V shape, right? Okay. And it overlaps with hydrogen, 1s, and here also 1s of hydrogen. Okay, remember, you must label all the hybrid orbitals. Yeah, sp3, 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 1s and 1s. Right. Okay. I think I stop here first, then I will continue with another video.